Hi all. All right, it's 3 o'clock, so I'll go ahead and get started. So I am Karen O'Neill, and I want to first off thank everybody who's online here. I appreciate you guys taking some time out of your day. The goal of this Zoom meeting is to just give people an overview of what's going on with the Green Bank Observatory. So we're going to start off with just a general update on the observatory itself. And then Toney will talk a little bit about what's going on in terms of instrumentation, as well as some of the scheduling and proposal handling and things like that. At the end of that point, we'll pause for questions, and then we will move on to Ryan Lynch, who's going to talk about what's been going on with the observatory in terms of pulsars. If you have any questions with any of this, please use the chat room. Rather than speaking out. We've got quite a few people onto this call, so it's going to be a lot easier if the chats, if questions show up in the chats, and then our moderator will step through from that and will read those questions out loud. And then second thing, please be aware that this whole talk is being recorded so that those folks who are unable to call in at this time or are unable to use Zoom for whatever reason, we'll be able to at least follow this talk. So with that, I'm going to go ahead and get started and step through these slides. So first things first, just for anybody who hasn't been following Green Bank Observatory lately, I just thought I'd spend just the first 2 or 3 minutes giving you a quick update on where we are in terms of the observatory funding, as well as operations and so forth. So Green Bank Observatory is an NSF FFRDC, as it has been since it started back in the 1960s. Just recently, and very excitingly, we're awarded a new 5-year grant for the next 5 years. So that goes through 2024. And this is a grant from the National Science Foundation to continue to be operated by Associated Universities Incorporated. Looking overall at the big picture budget status for Green Bank Observatory, our current funding is a mixture of both federal and non-federal funds. The bulk of our funding comes through our cooperative agreement from the National Science Foundation. Then the next group of funding comes through the Breakthrough Listen Foundation. So this is to actually use the GBT to go look for extraterrestrial intelligence and look for technosignatures out there in the universe. The Nanograv Physics Frontier Center, which is actually funded through the NSF to be a Physics Frontier Center, is the next largest group using our funds, and they purchase about 5% of the GBT time. And then the remaining funds come from a variety of different sources, universities, and other organizations. Looking at all of this, what does this really mean for things like open skies time? It means that the amount of open skies time on the GBT is about equal to the amount of funding coming in from the National Science Foundation for a cooperative agreement. So that means it's about 4,300 hours per year. So that's kind of the big picture of the GBT and where we're at. Just as a reminder, I don't want to spend a lot of time on this. The GBT is an absolutely fantastic telescope. So if there's anybody on the Zoom call that hasn't proposed to use the GBT recently, you absolutely should. Frequency coverage from 0.2 up to 116 gigahertz. And this is a bit of a messy slide, but hopefully you can see it on your computer screen, just showing the type of fantastic sensitivity that we get with the GBT across the frequency range they cover, as well as circling a couple areas where we have multi-pixel instruments up on the telescope. So that's kind of my very, very brief background of the GBT. And now I will go on to the primary purpose of this talk, which is an update on where we're at. So for those of you that are not familiar with what's going on in the US and in West Virginia, within the US, most of the regulations in terms of underneath the pandemic are being left to individual states. Within the state of West Virginia, our governor has issued what's called a stay-at-home order. So that's closing all of the non-essential businesses, closing the schools. In fact, just today, the schools were now closed for the remainder of the school year. As of about an hour ago, West Virginia had 914 confirmed cases of COVID-19, with about just over 1% of the state's population having been tested. And of those tests, 4% of the tested population is positive. Pocahontas County, where Green Bank Observatory exists, currently has no confirmed positive cases of COVID-19 within it. And we're incredibly fortunate to be able to say that at this point, across the state, our hospitals are not overwhelmed with cases. They've been able to keep things going. So Green Bank Observatory. Green Bank Observatory has been able to continue operations. We'll go into the details of what that means in a little bit. We are incredibly lucky and incredibly thankful that the National Science Foundation funding has continued unabated during this time. That means all of the Green Bank Observatory staff are receiving full pay across this time period. This is certainly very rare within this county, and we're incredibly thankful for the National Science Foundation for doing that. So what does operations mean for Green Bank? Well, we do have a skeleton crew that are coming into work on a regular basis. Telescope operators, we have one telescope operator in at all times, so they are continuing to work their 12-hour shifts and continuing to fully staff the control room. We also have a safety officer and a head of safety who are on site on an almost daily basis, just checking through, making sure everything is okay, making sure we're able to continue to work. We have a team of telescope mechanics as well as electronics engineers who are coming on site as necessary to perform the general maintenance tasks that we need to just keep the telescope running. And then we also have a skeleton crew from our plant maintenance staff who are coming on site to just continue to meet all of our federal regulations in terms of running the facility. Most of our staff, however, are trying to work from home as best as they're able to. That's what I'm doing right now. This has got all the normal challenges of working from home, as I'm sure everybody on this call is incredibly aware of. So, of course, we all miss working closely with our team members and are finding creative ways to do that. We have challenges in terms of the hardware and coming in to not be able to work with the hardware, as well as not to have our machine shop open and our electronics lab open. And of course, we still have documentation that is actually contained in paper that we need to access and are trying to find ways to do that. Like most places around the world, the schools and the daycare in this area are closed, so that's adding a little bit of extra complication. And then one of the bigger issues that we're running into with the work from home is just the poor internet connectivity across Pocahontas County and poor internet reliability in the area. This is an issue that Green Bank Observatory has worked for many, many years to try to improve, but it continues to plague the rural parts of West Virginia. So the result of that is that work is continuing across the observatory, but it's continuing at a much slower pace than it would be if we were all able to be in at work and working together. Before we get into what's going on with the GBT itself, I just want to mention education and public outreach. This is a huge part of what we do. It's something we're very, very proud of what we do. And it's something that is probably the hardest hit in terms of the programs within the pandemic and the COVID situation. So we have no visitors on site and have had no visitors on site since March the 15th. Our visitor center is, of course, completely closed. All of our education programs are canceled through the 1st of June and are beginning to be canceled after June 1st on a case-by-case basis. We are going to be able to run our summer research experience for undergraduates programs as well as our other summer internships. However, they will be run remotely. So our students will be working from their home or their home institution and working remotely with our staff. Camps and programs, all of our summer camps and programs, absolutely fantastic camps and programs, are being looked at individually, and looking forward into June, we're starting to see some of those starting to get canceled. And unfortunately, our 20-meter telescope, which is our remote educational telescope, is currently offline due to some issues that came about from power outages. So that's the bad news. The good news is that our education and public outreach team are absolutely being fantastic. They're finding all sorts of creative ways to work from home. They're looking to take a lot of the programs that we typically offer, and they're offering them online. Through a lot of this is advertised through our Facebook page. So you're seeing talks. We have Facebook Live interviews with the staff. They're looking to move a lot of our astronomy lessons online, building at-home activities, and so forth. So they really are, as many educational groups are, looking to find ways, creative ways, to reach out to the community and offer what we can online. So turning to the GBT, as I mentioned already, observations are continuing 24 hours a day, 7 days a week, with the exception of a weekly maintenance day that we're having that typically lasts anywhere from 4 to 8 hours each week. We are focused on keeping our staff safe within all of this, and that is the priority we make when we're looking at the decisions on what we can and cannot do with the telescope and across the site. So the result of that is currently only the absolute highest priority work is being completed right now. This means that there have been no receiver changes since early March, and none of the optional work, the nice to have work, is being completed at this time. What does it take to keep the GBT running? This is a fantastic example of this. Our latest real challenge that we've had within the pandemic time was a series of power outages that hit the county on the 8th and then again on the 9th of April. This required the restart of a lot of systems, a lot of computing systems, internet on the site, things like that. We slowly put things together, pieced things together, and in the process discovered that the azimuth encoder for the GBT had been damaged. So some of our staff, working very closely with safety, had to come up with a way to go and work on this system. Unfortunately, our azimuth encoder is in a very small room we call the pintle room. And the airflow in that room is not fantastic, and the people working in that room have to work very, very close together. And so we were able to, working, as I said, with safety, gather together enough personal protective equipment to bring two of our staff engineers on site. We actually put together a full airflow system down in the pintle room to allow them to work down there safely. In all, the GBT was offline for about 5 days due to a number of equipment issues that we had, but they were able to finally put the new encoder in place, get the GBT fully operational, and then tomorrow they're going back in, putting back on the bunny suits, and revising the entire electrical grounding scheme for the encoder tomorrow. So to me, this is just a fantastic example of our staff being able to work patiently, find a path forward to keep things running at a time when, as we all know, things are very complicated. So with that, I'm going to hand this off to Toney Minter to start talking about the Open Skies operations on the GBT.
All right, good afternoon, everyone. As Karen mentioned, we haven't done any receiver changes since our status with COVID-19 is operations have begun, though we are currently working out the procedures and priorities for being able to do that work. Hopefully we'll be able to do some of the changes coming up that are planned coming up in May. But also during this time, we've had the refrigerator seize up on our X-band receiver. It's currently awaiting repairs. Hopefully that'll be something that we can get to in the near future. Unfortunately, Mustang 2 had issues with its pulse tube, and that's pretty much shut it down for the summer. It'll be until we have regular access that we can really bring Mustang down off the telescope and proceed to lab work to get it repaired. And also, as part of the power outage that we had earlier in April, Guppy is now offline, and that's going to be a permanent thing at this point. So people with Guppy data should be moving it off the machines at this point in time. There's just a limited amount of time it'll be available. All right. So as far as scheduling goes, we're operating the telescope normally at this point in time. Only slight difference is that there are no on-site observers, and with that, there's no on-site observer training. That throws in a little extra twist for some projects, but we were working with those projects to try to come up with remote observers or alternative solutions for those projects. And the other aspect of that is our single dish school and observer training workshops that were scheduled for this spring have been pushed off until the fall. But if you do have a project that can't observe because you don't have any remote observers, please contact your project friend and we'll start helping you figure out how we can provide a solution. Proposals or the review process is continuing remotely. The TAC meeting will be later this week, and then we have several other reviews to go through and get things in order, and everyone should know the disposition of their proposals around mid-May. So everything's proceeding on course for that as far as the proposal handling. Go to the next slide. So as far as our new instruments that we're working on, Lassie, which is a laser scanner that be used to measure the GBT surface and much quicker than our current auto OOF procedures. That is hopefully will open up some daytime high frequency observing also, and would make more hours available for high frequency observing as a consequence. The work on that continues. They do have it set up in the lab so they can continue running tests and working out algorithms and various coding structures with the Lassie while we're in the shutdown process. It has delayed the machining of a weather enclosure so it can be installed permanently on the GBT at this point, but it shouldn't be causing any delays for the deployment of this instrument in 2022. We are building a new X-band feed, bringing it more up to date and bringing the cryo systems in line with all the other receivers. The design work for that has been completed during our current status, but is now being delayed because being able to have access to the machine shop to machine new parts. This will probably push out this project maybe a quarter to half a year further, and so we're looking at early 2021, possibly maybe towards the middle of the year for commissioning that receiver. So that work's being delayed a little bit. Then with the ultra-wideband receiver, Ryan will discuss that coming up here in a little bit, along with the improved digital signal processing for RFI excision. So why don't we pause at this point and see if anyone has any questions.
Hi, Tony. There was one question asking about which receivers were on the telescope. Amber responded in the chat, but if you want to speak to that in audio, you can do that now.
Yeah, what we had to do deciding going into our current operation status is which were the primary receivers that we would need to meet our sponsors' obligations, along with most of the observing. So we went with Prime Focus 800. LS and C, our KFPA, are always up. X-band was up, but it failed. We have Argus that's up, along with Mustang 2, which has also failed. So we're down 2 receivers at this point. And as we go forward, we'll look at whether we'll be able to change out the holography receiver and get the KA receiver up sometime in May. And it would be possible to change prime focus feeds in the future.
So I notice we also have a question on the current X-band system and the time frame on which it would be available again. I can answer that. So let me just say that we do have a process to move forward in terms of how to change the refrigerator safely and while protecting the staff. So our current issue, as it is in many cases, is just a decision we're trying to make regarding the use of very limited protective equipment that we have on site. And so if we find an urgent need, if there's a proposal coming in that absolutely needs to use the X-band system very soon, that our time allocation committee feels is important, we can go ahead and change that refrigerator. At the moment, now that we have a procedure in place, we can change that refrigerator if we absolutely needed to. So I'm not really answering the question about exactly when it'll be up again, but I guess if there was a proposal coming in, if we had a DDT or something else that had an urgent need, we would certainly weigh that against the other work that needs to be done on site to make a decision about putting the X-band receiver back up.
All right, if there are no other questions, we can move on to Ryan's presentation.
Everybody will have to be patient for just a moment as we switch computer screens here.
So I should be sharing my screen now, and there's my slides. So if no one interrupts me, I will assume that everyone can see the first slide, and I'll just kind of jump right into it because I am cognizant of the time. So just a few recent developments to go over. So as Tony mentioned, after many years of doing really outstanding science, Guppy backend has reached its end of life. So we had a system disk failure in one of the nodes following the power outage. So at this point, all observers should now be using Vegas. You should be getting any remaining Guppy data off disk. So the data disks are still accessible. And if you have any questions or need any help with that, just reach out to me or your project friend, whoever that is, may very well be me, and we'll be happy to assist with that. And I just want to give a tip of the hat to all the people who made Guppy such a wonderfully successful instrument over the years. So what I really then want to focus on is a couple of really fantastic new projects that we are currently doing, even in the age of COVID-19 restrictions. On a new ultra-wideband 0.74 gigahertz receiver for the GBT, which is really optimized for high precision pulsar timing, as well as some research and development into kind of complementary digital technologies for that receiver. And if I have some time, I'll show some fun work on active RFI identification that we have been pursuing as part of that. So the ultra-wideband receiver is funded by a grant from the Gordon and Betty Moore Foundation to support the work of the Observatory and Nanograph Physics Frontier Center. I put some technical specifications up here that people can read, but the real takeaway message here is that we're trying to increase the timing accuracy for high precision pulsar timing projects like Nanograph by as much as a factor of 2. And we get that through a combination of increased signal to noise, more precise measurement of dispersion delay, and better overall observing efficiency. So this is going to be installed as GBT's prime focus as opposed to the Gregorian focus. So we expect that it will kind of take over a lot of the work that is done for some of our low frequency receivers for pulsar work, as well as some of the higher frequency receivers. So I'm going to show a series of engineering drawings here, which is fun, and it'll kind of set the stage for showing some actual pictures of work which has already been completed on constructing the physical feed. So this is a quad ridge design with a dielectric insert, and I'm showing one of the ridges here along with this dielectric insert. It's very similar to the ultra-wideband feed, which was developed at the Parkes Observatory and which has now been commissioned there, if anybody is familiar with that. So there are going to be 4 of these ridges, which are shown in the drawings here. The little holes are just for weight saving. So these are not actually going to be visible because we're going to have the actual feed horn constructed in segments, which grows out that far, which makes up the primary portion of the feed. It's just a different view looking down inside of it with this dielectric insert. And then you can see the feed horns as they actually fall along the edge of, or sorry, the ridges as they fall along the edge of the feed horn. It's rather large. The opening aperture here is about 60 or 37 inches in diameter. It's about 60 inches long. We estimate it to be about 135 pounds. But there's actually more components to it than that even. So in order to perform well over a wide range of frequencies, we have to be very careful about controlling the beam shape as it falls on the telescope dish and making sure that we control spillover onto the ground so that we don't increase the overall system temperature. And so as part of that, shown in the green circles on these drawings, we have a set of aluminum rings called corrugations that help to narrow the beam at lower frequencies. And so the overall diameter of this is going to be about 80 inches. It's going to be quite large. Also shown in the drawings on the left is the vacuum window, which is the blue portion with the little red ring around it, as well as the back end box that will house a lot of the electronics and the refrigeration components, which is shown in the yellow portion up at the top there. On the right-hand side, there's just an alternate drawing where we see that the vacuum window is actually located at a slightly different location in the receiver. And this is actually the design that we're going with now. It still allows us to cool all the critical components, and it makes the vacuum window smaller, which makes it a lot easier to construct. So here's some actual pictures, which are always fun to show. So this is showing a test setup for the vacuum window prototype. This is just an 8-inch prototype. One of the biggest questions, because this vacuum window was basically designed in-house and needs to survive pretty high pressures because it is going to be so large. So we had questions on just what the best design was and whether or not it would actually be strong enough while still also being thin enough to have good transparency at radio frequencies. So Bob Simon, one of our engineers, designed a kind of cap of a hemisphere for the actual shape of the window, and a novel technique for actually building it up out of kind of interwoven fiberglass components. And it was set up here for destructive testing in a pressure vessel. Here's the results of the destructive testing. It was supposed to fail at some point. It's not infinitely strong, and it failed exactly at 65 PSI, which for this scale down model is exactly where it was predicted. So that's fun. I was unfortunately not able to be here when this was done. I was told it made quite a nice boom. We are also, or were, before the COVID-19 shutdown, actually starting to cut aluminum so you can see some of the rings here, which will go into the different segments of the feed horn, also set up in the machine shop. So the machine shop has been doing really excellent work figuring out how the machine, what is a very large and kind of complicated shape. You can see that we actually have components of one of those ridges on the right-hand side is Steve White, the head engineer for this project. Holding on to one of the ridges. So this is kind of the first one to roll out of the machine shop, more of a prototype. And you can see it kind of is put together in 3 different sections there. And then there's also, I mentioned the dielectric insert. So this is a quartz sphere that was custom machined by an outside company with Steve holding it again there. So this is going to sit down inside the feed horn and actually be vacuum cooled. And it was really cool to see this come in. It was actually pretty difficult to find a company that was willing to try and make a pure quartz sphere that would meet our specifications like this. So it was a lot of fun when we got that in, basically just before the COVID-19 shutdown started. So where are we now? Well, the machine shop work is currently on hold during this infectious disease operating shutdown. But we're hoping that we can ramp back up on that as soon as it's safely feasible. And we are looking at options for how we can do that so that we can move forward on the actual machining of the physical components. At the same time, though, there's been a lot of work that we are able to do remotely. So the Vegas backend is being fully expanded to enable coherent dedispersion over the full bandwidth provided by this receiver. And if you're not familiar with coherent dedispersion, it's just kind of a special pulsar observing mode that requires a significant amount of computational power. So we have several new machines decked out with the latest GPUs that are currently undergoing kind of shakedown and testing, and our software team continues to do development on the software manager side of things and all of the work that will actually go into controlling the physical receiver itself as well as the backend systems. We're making good progress, or we were making good progress before it shut down on additional electronics work like the amplifier testing, design of the IF system. And so we're still targeting scientific commissioning for the receiver sometime in 2021. And we'll see where that falls exactly based upon the kind of timeline for being able to get back fully to work. I also want to talk a little bit about a kind of complementary project that is being funded via an NSF ATI grant to the observatory. So one of the concerns with a receiver operating over these wide bandwidths is radio frequency interference, or RFI. And we completed a census early in the project, giving historical data. And we've designed some filters into the system to remove the strongest RFI sources. And we're confident that the remaining sources that are not being directly filtered out will not saturate the amplifiers, and that the electronic systems will be able to handle it. Nevertheless, it's desirable to digitize the signals early in the signal path as you possibly can to avoid analog components. And so the focus of this grant is to research and develop new digital sampling boards that can be eventually integrated directly into the receiver to sample at radio frequency, as well as to investigate some novel radio frequency interference techniques. So our electronics division has finished some initial testing of a 12-bit 10 gigasample per second analog to digital converter that will be able to digitize the entire receiver bandwidth in the single shot without any additional frequency conversion or splitting into multiple subbands. We're fairly confident it will provide the dynamic range for that. At the same time, we also have digital engineers that are developing firmware to interface this ADC with the newest Xilinx FPGAs and to enable 100 gigabit Ethernet working to actually transport the digital signal. And we are designing a custom printed circuit board that will actually interface the ADC to those technologies. At the same time, we've been exploring some novel RFI identification and excision techniques using machine learning and also cyclostationary signal processing. And that's what I want to spend the rest of the time talking about a little bit. So cyclostationary signal processing applies to classes of signals whose statistical properties are not time invariant, that is, they're not stationary, but they're periodic or quasi-periodic. So human-made information carrying signals have this property because of the way that we encode information. Pulsars are an astrophysical source that are also cyclostationary. But if you calculate the kind of cyclostationary properties of different signals, there's a rich set of information that you can extract. And I'm going to show some plots that I did not make and then a little movie that I did make to kind of demonstrate that. So what I'm showing here is something called the spectral correlation function. It's the cyclostationary analog to a typical power spectrum. And in fact, the power spectrum falls along the 0 alpha axis there at the top hand of this plot. This is for a theoretical phase shift keyed signal with a rectangular pulse. You can have different information encoding schemes as well as different pulse shapes. And that gives you, let's see, here we go, different shapes in the spectral correlation function domain. So you can see here, this is the phase shift keying algorithm, and you can actually see it jumping around to the different frequencies that it's using. Sorry that some of these disappear. This is actually a captured signal coming from a website called cyclostationary.blog, run by an engineer named Chad Spooner, showing a spread spectrum signal actually captured. And so this is real data, not just a kind of theoretical signal. Sorry, these plots keep disappearing. This is one for a CDMA signal, and then this is a rich feature set showing a bunch of different human-generated signals all kind of overlapping with each other and all of the different information that you can potentially extract out of this. So if you can calculate something like this in real time, you can potentially identify sources of RFI that are corrupting your data and distinguish between them. And I think that's a really exciting possibility going forward for doing online identification and removal of RFI. So I'm going to show a little movie here, just showing some early results from some code that we've developed and some real GPT data. So for this, we extracted just a single channel of complex voltage data, which is falling inside the iridium band. The native sampling rate was 1.28 microseconds. And I'm only going to be showing the spectral correlation function for sort of the top hits in modulation frequency or cycle frequency that were blindly detected by an algorithm that is well known within the literature on cyclostationary signal processing and that we did the Python implementation of. So the movie here, I'm just gonna see if I can, nope, can't really pause it, I guess. So I'll just let it play. So at the top, you're just seeing this single channel of voltage data kind of stream by, and the little area between the two blue bars is actually what's being analyzed to create the plot down below. And you see that most of the time, it just looks like noise, but every now and then you get a burst of about a 10 millisecond duration of RFI. And when that happens, if you look at the bottom plot, you'll see all these interesting structures kind of pop up. I think we're in a little bit of the RFI free portion right now, but another little burst will be along here. There's another one. So the idea here is that you eventually would be able to implement this with more optimized parameters. And again, hopefully moving towards a real-time system where you would be able to identify segments of the data that were impacted by RFI on very short timescales and extract them and remove them. So you're still going to be losing some portion of your data, but instead of losing an entire frequency channel that's contaminated over the timescales that we typically accumulate an average for, you might be able to recover some fraction of that data again at those frequencies. And in a way which is fairly transparent to the user. So if we're operating on real baseband voltage data in a non-recoverable kind of way, we certainly want to very rigorously test the algorithms and make sure that we know how they influence the final astrophysical data that we're interested in. And so that's another one of the things that we're doing right now as part of this grant, is developing a very rigorous testing procedure for these types of algorithms. And that, I'll just say that the long-term goals would be eventually to implement this in a kind of phase 2 portion of the project where we would then actually be able to digitize the entire bandwidth of the ultra-wideband receiver and incorporate some of these novel RFI identification and excision algorithms. And so I'll just throw some acknowledgements up here for the various different funding agencies and people who have helped with this work. And with that, I will see if there's any questions. Thank you.
We have one question here, Ryan, from Harshals. Says, what are the prospects of extending ultra-wideband and RFI excision capabilities to other receivers?
So that's certainly something that we want to do as well. I think that there's potential to kind of improve the actual instantaneous bandwidth that we can get if we can bypass some of the current analog components. And so for the first stage of the project, we just focused on a system that would be complementary to the ultra-wideband receiver. And then in stage 2, we're thinking we would actually try and implement that. And then I think once we've actually done that as a real on the telescope proof of concept, we would then turn our attention to trying to implement the same types of technologies in other receivers where possible.
All right, this time there aren't any other questions.
Okay, I'm going to go ahead and stop sharing my screen then.
So if there are no more questions, this is Karen O'Neill again. I just want to once again thank absolutely everybody for taking your time out of your day to find out what's going on with Green Bank Observatory. And to just let you know that if you have any questions about what's going on, we are trying to keep our web pages updated, or you should reach out to any of the scientific staff or any of us and just ask us questions. I see 2 more questions as I'm closing down. 2 more questions came up. We'll start with the first one. Ryan, if you're still on. First question is, what is the anticipated demand for other work besides pulsars?
Sorry, I'm not sure if I understand if that question is related to one of the existing projects or is it kind of the science case?
Could you use the, for example, the RFI excision capabilities for spectral line observing?
Oh yeah, absolutely. So yeah, that definitely would be the case. And then for the ultra wideband receiver, when you open it up to such a wide bandwidth, there are some trade-offs you have to make in terms of kind of system temperature and overall sensitivity. But for projects that would benefit from having that kind of very wide instantaneous bandwidth for spectroscopic surveys, regions that are very rich in molecular lines, then I think that there's also some real scientific potential there for the ultra wideband receiver. So both of these projects are kind of being motivated. Well, the ultra wideband receiver is primarily being motivated for pulsar work, but there's certainly a secondary science benefits there.
And then the second question was whether or not we could say anything about the GBT's planetary radar transmitter project, and I can talk to that. So the GBT is working with our partner Raytheon to look into the possibility of putting some transmission onto the GBT. The current project is a very low power system. It's going to be deployed purely as a test case to see what can be done using a variety of different technologies on both the transmit and the receive side. So that is a project that we're working on, and we anticipate all things working out well, depending on delays due to the current pandemic. Being able to have a very low power transmit system on the GBT sometime this fall. This is not something that will be useful for planetary radar. Again, this is a test system to try to understand things. Building off of that, we will be looking into the possibility of building a more powerful transmit system on the GBT. This is that would potentially have the ability to work with the planetary community for some of their radar systems. This is still a TBD. It's something we're very interested in doing, but not something that we have definitive plans for in terms of frequencies or exactly what would go onto the telescope. We are actively seeking right now a scientist or engineer to help us lead this project forward and to start working with the communities that would be interested in this transmitter to really pull together the requirements and make sure we're building a system that's of interest to everybody. Again, that's a pretty hand-wavy answer, but that's because it's very early days with us. So low power transmitter absolutely going on to the GBT to test some ideas and concepts this fall. And as we hopefully fill this open position, we will be able to start moving forward and working with the planetary community. We were certainly hoping to attend the workshop in June, which I think is still scheduled, to talk more with the community about this, but it's still a lot of TBD, and certainly we'd be reaching out to the planetary community as we move forward on building the requirements for it. Okay, so with that, again, I'm going to thank all of you guys for your time very much. Please reach out to us if you have any questions, and I believe that Jay Lockerman will be looking in a couple of weeks to potentially schedule another one of these to focus on other aspects of the GBT. So thank you guys very much again for your time. Bye-bye.
Thanks,
Thank you, Karen and staff.
Thank you, everyone.
Thanks a lot.
Thanks a lot.
Thanks.